load scheduling algorithms that use a linear solver with the linear program I just showed you are as follows. We have FIFO, which is first in, first out. As you can see there, the allocation and collection orders are identical. Then we have LIFO, which is last in, first out. And you can see there that the collection phase is just the reverse of the allocation. Then we have our OPT algorithm, and what this one is the optimal solution. What it does is it tries all combinations of allocation and collection. So if we actually had like 5 processes in our system, it would try 5 factorial squared different combinations of allocation and collection. Now, that gets to be, really costly in time. Like if our system has like 16 processors, that would take days to calculate. So, to alleviate that cost and time, there was a heuristic algorithm known as I2LP created. And though it doesn't perform optimally in all cases, it does perform near optimal, and it takes a lot less time to calculate. Now I'm going to describe the I2LP algorithm. You'll see the authors up above, and it's actually a relatively new algorithm. It was introduced in a paper for a conference known as Heterogeneous Computation Workshop, and that was in April 2008. Now, the steps that the algorithm takes are as follows. We have it starts by sorting the processors that are given to it by increasing C values. And what I mean by that is the longer it takes. Like by increasing C, the larger it is, the longer it will take for data to pass through, essentially. So the second thing it does is it solves linear programs for all combinations of allocation and collection for the first 2 processors. And after that, it iteratively adds the remaining processors one by trying all possible sequences, but also retaining the best sequence from the previous allocation and collection. You'll see there that I have an example for the first 2 processors. Now, if that happened to be the best allocation, then when we add our third one in, you'll see, oh, this is kind of messed up. But the allocation of the third processor gets interleaved or sequenced throughout what was throughout what our best one was previous. So rather than trying all combinations, it takes a few less steps. And in any given iteration, if there are k processors being used, there will be k-squared linear programs solved, rather than k factorial squared compared to the OPT. And the final thing it does is, if there is 0 load given to a processor when the best time is returned in any given iteration, then the I2LP will actually halt and just produce whatever time was best at the time and give all of our appropriate load fractions. Otherwise, the algorithm will keep going and finish with the last iteration and best time and load fractions. So basically, I wanted to modify the I2LP2 algorithm, or the I2LP algorithm, and make a new one. And I've done 2 modifications to it. One is to try different sorting algorithms. And rather than just sorting by C, I try sorting by E, our computation, by both C, then E, and also by L. And my other modification is the addition of the latency parameter. And I do it with 2 different methods. One is in I2LP2A, and what that does is it adds the latency in after the linear program has been solved. And the I2LP2B adds the latency into the equations that you saw in the constraints, and it solves the linear program that way. So my goals are to show the limitation of I2LP after latency is added, and then to show the cases where I2LP fails when C values are the same for all processors, like in a case where you have a cluster network, where you have like say 16 processors in a cluster, and they all share the same bandwidth and the same processing speed. So what do you do with that? And then I'm going to show where the different sorting algorithms are best suited, as well as finally showing that ITRLP2A and B outperform ITRLP in all cases. Now, I did this by running a few different experiments. The first one is 100 simulation runs using different ranges of randomly generated system parameters for C, E, and L. And I also did a cluster experiment, actually 2 cluster experiments, one that favors sorting by computation and latency, and the other one that favors sorting by communication or communication then computation. Now, here are the system parameters for simulations for the 100 samples. You see here we're doing it for 5 processors, and we have a result factor of 0.5. And the ranges for C, E, and L are 1 to 100, 1 to 1,000, and 0.01 to 10, respectively. Now, this is the result of the simulation run. Excuse me. You'll see that I'm only showing the 3 algorithms, ITRLP and my 2 modified algorithms. And they're all sorted by C. So you'll see here that the optimal time for the ITRLP appears to be well above ITRLP2A and B in most cases. And my 2 modified algorithms are relatively close together. So it can be concluded from this graph that with random parameters that ITRLP fails to produce near optimal times. So here is another representation of that, and it's using box plots. And obviously ITRLP is not doing so well, being way up there at the top. And all of the rest of the different sorting algorithms do relatively the same, just with random parameters. Now for the cluster experiments, I began with a cluster, 4 clusters and 4 processors per cluster, and the result factor is 0.5. And you'll see here that we have our 4 clusters and all of their parameter values listed here. You'll notice that cluster 3 and 4 have C values that are lower than cluster 1 and 2. So ITRLP will actually favor that before the other 2 clusters. But the problem with that is that the latency is way higher. It's very, this algorithm is very sensitive to latency. So you'll see here with the results that ITRLP is way up top with that blue bar, whereas my other 2 algorithms with sorting by E and L are relatively low. In fact, L is less than half the time to schedule loads. So it can be concluded from this graph that when sorting by E or L with my new algorithms, that it is best suited. Also, ITRLP is still doing much worse, as I had stated before. So with the second cluster experiment, it's essentially the same for the parameters up here, except I changed the clusters a little bit. You'll see the L values are all 10 now. And so when I do a sort by L, it will actually just take a shuffled set of processors. It all depends on what the algorithm is receiving. You know, it could be in any order. So that can vary. It depends. It could be a really good time, it could be a really slow time. So you'll also notice that the C values and E values are relatively close together and not too far off. So from this, the results of this cluster experiment show that ITRLP doesn't do too bad, but it doesn't do too much better. Or it doesn't do too bad. Yeah, that's what I'm trying to say. And the other algorithms, in fact, when they sort by C and C then E, they did better, but not too much better than the